Have you ever been scrolling online and seen one of those videos of a humanoid robot dancing with moves that look almost human? And you just have to ask, how in the world is that even possible? Well, today, we're going to pull back the curtain and find out. We're going to demystify exactly how these incredible machines, like the ones from Unitree, are learning to master such complex human skills. It really all boils down to this one central question. Think about it. How do you teach a machine made of metal, wires, and actuators with a totally different body plan than yours to do something as fluid and natural as dancing? That's the core challenge, and we're going to unpack it piece by piece. So, to understand how our robot learns to dance, we first need to zoom out and look at a huge shift that's happening in AI right now. See, AI isn't just about crunching data in the cloud anymore. It's getting a body, it's moving into the physical world, and it's learning to interact with our reality. And there is a name for this: physical AI. Some people call it embodied AI, but the idea is simple. It's what you get when you combine an intelligent software brain with a physical body that can see, touch, and move around. This is the absolute foundation for any robot that needs to work in a complicated human-designed world. So what we're really witnessing here is AI breaking out of its digital cage. Instead of just analyzing text or recognizing images, it's learning to walk, to balance, to adapt, and yeah, even to dance right here alongside us. This is a massive leap forward. But there's a catch. Before that robot can learn anything from a person, it has to deal with a really fundamental problem. You can't just copy and paste human movements onto a robot's body. There's a huge, huge gap between how we're built and how they're built. Which leads us to this question, right? If you just told a robot, hey, copy that dancer, it would probably fall flat on its face. Why? Because its body has totally different limitations and properties. And this problem has a name. Engineers call it the embodiment gap. And this chart breaks that gap down perfectly. Just think about it for a second. We have flexible spines and incredibly complex feet. A robot has rigid links. Our weight is distributed in a unique way. A robot has a completely different center of gravity. We can move our joints in all sorts of ways. Theirs are much more constrained. These aren't just little details. They're fundamental differences that make a direct one-to-one copy totally impossible. So how do you solve a problem that big? Well, engineers have come up with a really clever and systematic process. It's a 4-step pipeline that takes a human performance and translates it into a successful robot dance. Let's walk through it. Okay, here's the whole roadmap at a glance. First, you capture the human motion. Second, you translate that motion to fit the robot's body. Third, and this is the big one, you use AI to teach the robot how to actually perform the moves without falling over. And finally, you take that learned skill and put it on the real robot. Step 1, it all starts with good data. They bring in a professional dancer and use motion capture systems. Mocap, the same kind of tech they use to make CGI characters in movies. This lets them record every single tiny movement with incredible precision. That gives them a perfect reference to work from. Now for step 2, retargeting. And this is where some real magic starts to happen. It's basically a sophisticated translation process. The software takes all that human motion data and mathematically adjusts it for the robot's unique body. It figures out, okay, how can the robot's shorter arms or its limited knee joints get as close as possible to the human's movement? This is how they computationally bridge that embodiment gap we were just talking about. All right, now we get to the absolute heart of it. Just having the retargeted moves isn't enough. The robot still doesn't actually know how to balance or react to physics. It needs a brain. And that brain is built using a powerful technique called reinforcement learning. Reinforcement learning, or RL, is a total game changer for robotics. Instead of engineers trying to hand code every single possible movement for every scenario, which is basically impossible, RL lets the robot learn for itself through trial and error. It moves the robot from just following rigid instructions to having real adaptive autonomy. So let's break it down with a simple analogy. Picture the robot inside a computer simulation like it's a character in a brand new video game. It has no idea how to play. So at first, it just tries random stuff to follow the dance moves. And as you'd expect, it fails. A lot. It's just falling and flailing all over the place. But here's the crucial part. Every single time it tries something, it gets instant feedback. If it moves a joint and it manages to stay balanced while tracking the dance move correctly, it gets a reward, like points in a game. If it gets wobbly or falls over, it gets a penalty.
And it does this over and over and over again for millions of attempts inside the simulation. It's basically building this huge experience notebook in its memory, learning which actions led to rewards and which led to penalties. And that notebook becomes its policy. The policy is the brain. It's the learned strategy that tells the robot the best possible move to make in any situation to get the highest score. And this graph shows you that process in action. It's a learning curve. As the number of training attempts goes up, we're talking millions here. The reward the robot gets goes up and up. This is a literal picture of the robot getting smarter, learning from its mistakes, and slowly mastering the art of not falling down while it dances.
Okay, so our robot is now a perfect dancer inside a computer. But the real world isn't a perfect computer program. It's messy. So now engineers face the final massive hurdle, making sure the skills learned in simulation will actually work on a real physical robot. And there's a very good reason we have to start in a simulation. As this quote says, trying to do this kind of trial and error learning on a real robot is just not going to happen. It would be insanely expensive and dangerous. Can you imagine a prototype that costs a fortune falling over and breaking itself thousands of times a day? It's just not practical. But training in a simulation creates its own challenge, and it's called the sim-to-real gap. The simulation is a clean, predictable, perfect world. The real world, on the other hand, is messy. It has things like tiny variations in friction or slight delays in sensors, all things that can trip up a policy trained in a perfect environment. So how do they solve this? With a really smart technique called domain randomization. Basically, instead of training the robot in one perfect simulation, they train it in thousands of slightly different ones at the same time. In one simulation, the floor might be extra slippery. In another, a motor might be a little weaker. They constantly change all these variables, forcing the robot to learn a policy that's tough and adaptable enough to handle anything.
And the result of all that tough training is a policy that is incredibly robust. It's not brittle. The ultimate goal, the holy grail, is what they call a zero-shot transfer. That means they can take the policy straight from the simulation, load it onto the physical robot, and it just works perfectly right out of the box with no extra fiddling around. So, we've gone through this whole complex process, and we have a dancing robot. But you might be thinking, okay, but is this just a really cool party trick? And the answer is a definite no. This is about so much more than just busting a move.
You see, mastering a dynamic skill like dancing is what you'd call a benchmark. It's a stress test. It proves that you've created a control system that is incredibly agile and robust. That ability to balance while doing a long, complex series of movements is the exact same fundamental skill a robot would need to, say, walk over rubble in a disaster zone, or quickly pivot to catch something you dropped in your kitchen. And that agility opens the door to so many real-world applications. A robot that can balance this well isn't just a dancer, it's a potential assistant that won't fall down the stairs, or a factory worker that can move nimbly around a chaotic floor. It's a huge step towards creating humanoid robots that are genuinely useful in our daily lives.
And that brings us to the final thought. This whole pipeline we've just explored, from capturing human motion to training in a simulation and deploying it in the real world, is an incredibly powerful recipe for teaching robots pretty much any physical skill. So it leaves you with a question. If they can master the art of the dance today, what truly complex human skill will they master tomorrow? Thanks so much for watching.